I am Edoardo Debenedetti, a PhD student at ETH, and today I'll be talking about privacy side channels in machine learning systems. This is joint work with Giorgio Severi, Nicolas Carlini, Christopher Choquette-Choo, Matthew Jagielski, Milad, Nasr, Eric Wallace, and my advisor Florian Tramèr. I guess if you're here and you stuck until now, you know that machine learning models leak training data. And this can range to a different type of attacks. We go from membership inference attacks, where an adversary is trying to understand whether a given victim target sample was part of a training set, to more complex and dangerous attacks, such as data extraction attacks, where an adversary is trying to get the model to regurgitate data. And these can be potentially dangerous for revealing private identifiable information. And this is a line of work that has been going on at least since 2017 with the first membership inference attacks against machine learning models. But what people have mostly done so far was to look at the model in isolation. So they look at the model, they look at the training data, and then only look at these two things, they try to leak, to make the model leak information about the data. However, what happens in practice is that these models are deployed within a much broader and wider, a complex system, which includes components in the training pipeline, components in the deployment pipeline, and this is really much more complex than just the model itself. And as such, when we look at a machine learning model as part of a broader system, turns out we can leak much more private information. And for this reason, what we do in our work is finding what, inspired by the traditional security literature, privacy side channels in machine learning systems. We call them side channels because instead of looking at the component per se that we are attacking, we're looking at other things that are around it and exploit it. And we find that there are side channels all over the place. From the training pipeline to the deployment one, with some examples in the training pipeline, data duplication and poisoning detection defenses, to memorization filters in the deployment pipeline, where memorization filters try to prevent the model from regurgitating training data, and even input filters at deployment time with detectors that try to prevent evasion attacks. And for the purpose of this talk, given that the time is limited, we'll be focusing on the first type, on data duplication and attacks by exploiting data duplication. Just to give a brief primer on data duplication, people usually do data duplication, as Jeremy said earlier, to improve the privacy on the training data, because previous work showed that duplicated data are more likely to be memorized by a model, but also to improve the performance of models. For example, the DALL-E model from OpenAI, they also observed that data duplication improved the quality of generations. And basically what happens is, this is a simple scenario in the computer vision domain, is if we have two images that are the same, then we delete them. This is, again, there are multiple types of duplication that can be done, and in the paper we consider several types, as we will also see later. But basically, this sample gets deleted, and then they're not used during the training of the model. And the attack that we do leverages data duplication in a fairly simple, intuitive way. What we do is adding a poison, so we add a duplicate. So let's assume that we're trying to target a model that is a binary classifier and is distinguishing between cats and dogs. What we do is we add an image that is a duplicate of our target. However, we give it a wrong label. So if our target image is the image of a dog, we are going to add the same image, but with the label of a cat. And we assume that the adversary can poison the data set. For example, in a scenario where a data set is crowdsourced from people. And so what we do is we add the sample with a cat of a label. And what happens is that if our target sample was collected together with our sample, then these samples are not going to survive the duplication. Now, this is a case where the duplication deletes all the data. We also consider the case where the duplication acts in different ways, for instance, by keeping one random piece of data. And so the samples gets deleted, and at training time, the model is not going to see them. So what's going to happen at inference time is that the model is very likely to correctly classify the image as a dog because it's a cute puppy, it's very nice, it's very in distribution, so there is no reason why a good model should classify this image differently, or at least with like good confidence. However, what happens if the sample was not in the training set, if our target was not in the training set, is that our poison is going to survive the duplication. And so the model is going to see our target with the wrong label during training. And since it's an outlier, it's very likely to memorize it. And so at inference time, it's going to classify it as a cat, very likely, or at least to give an abnormal confidence that this image is a cat compared to the previous case. And so, as I guess you may have understood now, what we do to distinguish between members and non-members is looking at what the model outputs after adding our poison. Because if the model outputs that the image is a dog in this example, or at least has reasonable confidence that the image is a dog, then it means that the sample was originally in the data collection and was duplicated together with other sample. However, on the other hand, if the sample was not there, then our poison is kept in the training set, and so the model is going to classify it as a cat. And yeah, this is fairly simple. This is a very simple scenario where we are doing exact duplication and deleting all the data. But let's make things a bit more interesting. As I mentioned earlier, people also do different types of duplication. Earlier, what I described earlier is called exact duplication, but what is done more realistically is approximated duplication, where basically we consider two images to be duplicates if some similarity metric is above a given threshold. And so what we do is we add poisons with a certain structure in a way that our poisons, which are the images that are around, are all less similar than alpha to each other, but they're all more similar than alpha to the target. And what's going to happen is that if the target is not in the training set, then all our images are all not similar to each other according to the similarity metric that is being used by the people who are training the model. And so all our samples with the poison label are going to be kept. However, if the target is in the training set, then we create this kind of cluster of duplicates, and then either all or all but one of the samples in the cluster are going to be deleted. And this creates a scenario that is similar to the one earlier, just in a scenario that is more realistic and a bit more complex and interesting. And we show that this actually works really well. So if we look at the true positive rate of our guesses for membership inference at the 0.1 false positive rate, our method gives near perfect membership inference at 96%, compared to previous work that also assumes the capability of the adversary to poison the data set that doesn't exploit the duplication, that is, if I remember correctly, around 42%. And so the duplication really boosts the performance of membership inference attacks if exploited properly. And so far we have seen that the duplication is used as a privacy defense, but it's a heuristic defense. It doesn't provide any sort of formal guarantees. And so what we could do is, okay, let's stack on top of the duplication something that actually gives us privacy guarantees, like differential privacy. And will putting these things together actually help? Will we get better privacy? And this is something that previous work even suggested at some point. And so how does it work? Basically, what people usually do is we have a model, we train the model using some differentially private method, and this model, if we look only at the model, is going to give us some privacy guarantee. So it's going to give us some number that says, well, no sample is going to have more than a given influence on your final model. And so again, if we look only at the model, even if you're using the duplication, we might run our attack and see that the privacy guarantee more or less aligns with what we expect. However, again, models are not deployed in isolation. They're not trained in isolation. And so we wonder, okay, if we consider the model together with other components, do we still get a privacy guarantee? As I guess you may have guessed, we actually don't. Because using the duplication actually violates some of the assumptions that are necessary for differential privacy. And so actually we show that the attack has a performance against what should be the differentially private model that shows that the privacy guarantees are actually at least 1,000 times worse. And so this is, we really show that it's important that even if we have something that is we believe gives privacy guarantees, and we are sure, well, we're definitely okay with this, then we still need to be careful with how we combine this. And as a general takeaway from the talk and from the paper, we really believe that people should think about, when they think about privacy, and not only in this case we are considering privacy, but this also applies to security, we shouldn't only consider the model in isolation. Like machine learning practitioners very often are like, yeah, okay, the model is here, but then we have a lot of other components. Actually, this is something that in industries there's more awareness than in research, where we actually mostly look at the model. However, again, models are deployed together with other components, and components could interact with each other in ways that we might not necessarily expect. Thanks a lot for listening. I'm happy to take any questions.